In just the last video, we took a look at these hurricane lanterns, their history, and how they work. If you haven't seen that, I'd recommend watching it first, because this video will be building upon it. Oh, real quick, someone asked for a simulated hurricane. I can't quite do that, but here's a leaf blower. Pretty impressive. Anyway, flat-wick kerosene lamps and lanterns were ubiquitous everyday sources of lighting outside of cities for decades, and unfortunately remain so across wide swaths of the developing world. While burning a fuel to create light is certainly not the best way to do it for a plethora of reasons, a development of the late 19th century made the process a whole lot more useful. This kerosene lamp is much brighter than any of the others we've seen so far, burns cleanly, and is green. And the technology that makes it so bright is what we'll be talking about today. But first, we need to step back from lanterns and talk about the town gas industry. Someone, and I don't remember who, so I'm sorry I can't thank you personally, recommended this book to me, Disenchanted Night: The Industrialization of Light in the 19th Century. It's a fascinating read and focuses mainly on the development of centralized lighting systems, both gas and electric. I had mentioned coal gas in the last video, and a number of you wondered what that was. So here's what that was. Also, we need to talk about it anyway. Before the natural gas we know today, gas that was delivered to the home was manufactured from coal and less commonly wood. It took me until last week to realize that's why we call it natural gas. Its predecessors literally were not natural. Anyway, coal can actually be processed into a number of different products, much like petroleum. And it was known since the late 17th century that if you distill coal in a retort, that's one of these mad scientist chemistry set things, not just a devastating comeback, one of the byproducts was an inflammable spirit. I'm going to quote from the first known written discovery of this phenomenon, written in a letter to Robert Boyle by amateur chemist John Clayton. This was in 1691. I got some coal and distilled it in a retort in an open fire. At first there came over only phlegm, afterwards a black oil, and then likewise a spirit arose, which I could no ways condense. But it forced my lute, or broke my glasses. Side note, I have no clue what forced my lute is supposed to mean. I also don't know if the or broke my glasses might be clarification done by Shivelbush, the author of the book. I googled the phrase forced my lute, and the only results were of this exact letter, many of them being quoted from this very book. I'm choosing to interpret it as one would grinds my gears or ruffles my feathers because that's fun. It's probably wrong, but anyway, to continue. Once, when it had forced my lute, coming close thereto in order to try to repair it, I observed that the spirit which issued out caught fire at the flame of the candle, and continued burning with violence as it issued out in a stream, which I blew out and lighted again alternately for several times. I then had a mind to try if I could save any of this spirit, in order to which I took a turbinated receiver, and, putting a candle to the pipe of the receiver, whilst the spirit arose, I observed that it catched flame, and continued burning at the end of the pipe, though you could not discern what fed the flame. I then blew it out and lighted it again, several times. As would I, Clayton. As would I. The discovery of this inflammable air, as it was often called, was a real mind-bender. What's burning? People asked. How can there be fire with no oil and no wick? Seemed like an impossibility and nothing more, but of course it wasn't. However, it would take quite a long time, in fact more than a century from when that letter was written, for it to be put to use. It was the factories of England, thanks to their owners who wished to see greater productivity out of their workers, where we could find the first permanent application for this wondrous stuff. Specifically, at Watt and Bolton of Soho. As it happened, the owners had already expressed interest in improved lighting technologies, and they knew Argand personally and used his lamps. But one of their associates, William Murdoch, would develop the coal gas production and storage methods which were to quickly become the standard. More or less. Oh, and quick side note, at basically the exact same time, a French guy named Philippe Le Bon was doing similar work and developed something called the thermolamp. But his idea centered around producing the gas at the hyper-local level. as in you would have a gas distilling apparatus in your home, and ultimately the concept fizzled out. Originally experimenting with balloon-like containers to store and perhaps even transport the gas, Murdoch eventually found that the only reasonable way to make use of this gas was with pipes to distribute it and so-called gasometers for storage, which, funnily enough, were devices conceived by none other than our old pal Antoine Lavoisier. Murdoch, by the way, is responsible for calling it a gasometer, which annoyed many scientists because it is not a measuring implement of any sort. Those with a particular keenness towards accuracy much prefer the term gas holder. Nevertheless, gasometer stuck around. Anyway, first done at the rather small scale of on-site gas production and storage for lighting a single factory, this idea quickly scaled up and spread out. As luck would have it, producing coal gas used basically the same exact process as producing coke from coal, which had already been in routine production for the high-temperature furnaces used in metalworking. In fact, the gas was a byproduct of the coke production process. So basically, we already had the knowledge and equipment for this new gas stuff, and just needed to tweak how the coal was distilled a little bit and make an effort to collect and store the gas. Before long, central coal gas supplies were feeding entire neighborhoods, and an imaginative revolution in lighting was swiftly upon us. This manufactured gas contained a lot of so-called illuminants, or components which helped produce a bright flame. I mentioned it in passing, but what actually makes the flame of a candle glow are small particles within the flame that are incandescing. That's a very complicated topic, and there are a number of reasons those particles can A, exist, and B, glow, but you'll only get a bright flame if there's something in the fuel which will glow brightly with the heat of combustion. A natural gas flame hardly glows at all because the fuel is quite pure and burns completely thanks to a well-designed burner. In fact, the blue color of that flame is the result of an entirely different chemical process. A flat-wick kerosene lamp not only burns a less pure, or you might say dirtier, fuel, but much more importantly, that combustion isn't as complete, so little bits of unburned fuel end up as soot, which will glow in the heat of the flame. The same goes for a candle, and for this new coal gas. By tweaking the coal distilling process and also by using different sources of coal, the illuminating ability of the gas could be maximized. And since the gas was already a vapor and didn't rely on a wick to evaporate and burn, the flames could be much larger without becoming sooty, and thus they could be brighter. A common design for a burner produced a sort of fan-shaped flame, and with a limitless to the user supply of fuel in the wall, brighter lights were easy to accomplish. Just add more burners as desired. The decades that followed saw countless designs for new lighting fixtures. We also developed the first light switches, which in this case were valves that could stop and start the flow of gas. Those quickly started being placed near the entry of rooms, pretty much exactly where we put light switches today. This coal gas infrastructure looked an awful lot like the electric lights that would replace them, in no small part because those electric lights were emulating how the gas ones worked. Now, just as it is today, gas lighting was unpleasant. Oh sure, it was marvelously better than candles, and when we first started using it, everybody was wowed out of their minds. But we quickly found its many problems. This coal gas was very toxic, and it was not hard at all to be poisoned by it. Unlike gas of today, there wasn't much pressure in the pipes, so you couldn't actually hear the gas escaping even from a normally operating fixture. This made leaks undetectable in many cases. Deadly gas explosions weren't exactly uncommon either, and the infrastructure which moved it around would pollute soil and groundwater when it leaked. Even when things were going well, we also ran into problems, because we were burning so much of the gas that we were using up all the oxygen in a room. There was a downside to more light. We just hadn't run into that limitation yet, because candles and oil lamps realistically didn't consume enough oxygen to be problematic. While we would eventually develop fixtures which had their own ventilation, This also helped cut back on how hot the lights made the rooms in which they were used. Even then, places which needed a lot of light would run low on oxygen. It was very common for people to find going to the theater to be an unpleasant, headache-inducing experience, because they were literally being partly asphyxiated the whole time. Oh, and also, if you've heard about how over time the byproducts of this gas would do things like darken walls and cover paintings in layers of goopy soot, well, that was also a thing. Over the decades, people simply lost their affinity for the stuff, and it's no wonder. And so now we are back to this. Up till now, more light meant more fire. We still relied on the illuminating particles in the gas to provide the visible light we wanted. But this was about to change. In 1886, Austrian chemist Auer von Welsbach invented the incandescent gas mantle, and it's what makes this lamp so bright. Here, we are simply using the heat of the flame to our advantage. We no longer care if it produces light of its own, we just want it to get the mantle very hot, which causes the mantle to glow. This principle was known long before Welsbach invented the gas mantle. Limelight, mainly used in theaters, was a direct predecessor. Here, a piece of calcium oxide, or quicklime, was heated to incandescence by an oxyhydrogen flame. If you want to see what that looks like, there's a video linked in the description, or you can check out the card here. Of note is that a second phenomenon, candoluminescence, is known to be going on here as well. This phenomenon causes certain materials to emit more visible light than a blackbody radiator would at the same temperature. And, well, the explanation on that is a little confusing to me, and honestly, it doesn't seem like the knowledge of the mechanism is entirely settled yet. So we're just going to acknowledge it's a thing and move on. What Welsbach figured out was how to make the same general principle of limelight work with the low-intensity flames of ordinary gas. Now, we need to make a quick clarification here. The coal gas of this time period didn't have to burn with a visible flame like a candle. Burners meant for lighting would of course do that, but with better control of the air as it mixes with the gas, a cleaner, hotter flame could be attained. This is what the Bunsen burner was designed for, and indeed, Welsbach would use Bunsen-type burners for his new gas mantles. And the Aladdin lamp makes use of those gas mantles. By the way, this is the same Aladdin lamp company that invented the touch lamp, so there you go. Now, I must admit that we are going a little out of order here. The gas mantle was in effect adapted for use in kerosene lamps like this one. Welsbach was working with Bunsen burners and coal gas, and this implementation actually has some significant drawbacks, which we'll get to. But for narrative reasons, I'm explaining it with this lamp first. If you noticed that the burner and chimney look very different from the Dietz lanterns and the dead flame lamp, well, that's on purpose. This tubular wick burner, which is not really an argand burner, again, that was a red herring, it just sort of looks like one. Anyway, the skinny and tall chimney combined with the hollow wick creates a central draft burner that burns kerosene much more intensely than these guys. If you noticed when I removed the mantle and showed the flames, how high they went, yeah, this is a very different animal. Atop the burner sits the mantle. Its lace-like appearance suggests it could be a sort of fabric, but it's not. However, it was. We'll get there. That part is extremely clever. In its current state, though, this is a very fragile lattice of, effectively, ash. This has very little mass, a large part of why it's so fragile, and it's made from... Did you know there's controversy regarding the phasing out of thorium in gas mantles? Some very picky campers certainly do, but most of you probably don't. Happened like 30 years ago. We'll talk about that later. But, right. Anyway, this mantle is probably composed mainly of yttrium oxide, which is a ceramic material with a very high melting point, about 2400 degrees Celsius or 4400 degrees Fahrenheit, or just shy of 2700 degrees Kelvin. Because it can get that hot without melting, it can incandesce brightly, and that means it will produce a lot of visible light when heated with fire. Take a look. Here's me holding a lighter to it. You see a glowing hotspot, pretty much as white as an incandescent light bulb, but you'll notice that it glows best near the hot blue part of the flame. If I switch to a torch-style lighter, which uses a burner not unlike a Bunsen burner, you'll see it makes a brighter and more uniform spot on the mantle. The best flame for illuminating the mantle is clearly a pure and hot one. Getting that sort of flame with kerosene and a wick is the reason the Audin lamp is somewhat special. The burner is able to do just that. In practice, you light this lamp by removing the entire top section, known as the gallery. This holds the chimney and mantle. That grants you access to the wick. Then you simply light it and put the gallery back on. Then, when you lift the wick, the strong draft created by the tall, slender chimney, along with the hollow wick and flame spreader, combine to create an astonishingly clean-burning, high-heat kerosene flame. The mantle's shape helps confine the flame and its heat energy so that it acts upon it as much as possible, and voila, a very bright, surprisingly usable kerosene lamp. And this burns so cleanly it's entirely odorless. Seriously, this is amazing to me. You really only get heat from this thing. There's no smell at all, and yet it's burning the same kerosene as these Dietzes. But its burner, while clearly unique, isn't the star of this show. The reason the mantle can glow so brightly, aside from the fact that it's made from a heat-tolerant material, is that it's so incredibly light. I wasn't exaggerating that this is basically ash. This stuff is hardly even there. Having such a minuscule thermal mass allows it to easily get to incandescent temperatures without relying on an oxyhydrogen flame as Limelight did. But if it's so light and fragile, how on earth are you supposed to install one? And why does it look like a tiny hairnet? Well, here's the clever bit. This mantle was a fabric mesh, but the strings which made up that mesh were coated in a solution containing salts of yttrium nitrate and potentially some other chemicals too. Here's a different mantle, which, spoiler, will come up later. This one hasn't been used yet, and it's soft, fairly strong, and quite flexible. The actual fibers that make up the mantle can be made of cotton, rayon, really a number of things, so long as they can soak up and retain the salt solution. The yttrium oxide doesn't exist yet in this form, but it will when we burn it. The mantle of the Audin lamp is a little different as it comes coated in this blue stuff which holds its shape. And when you set light to it, this happens. That initial burn-off converted the salts of yttrium nitrate in the fibers into solid yttrium oxide, and also burned everything else away. Normally, the mantles don't just up and whoomp like that. That blue stuff, I'm not sure what it is. It might be collodion or possibly celluloid. Let us know if you know. It accelerates the process greatly, but the end result is the same. The ghostly remains of the newly formed yttrium oxide and pretty much nothing else. It takes the form of the fabric net because that's where the nitrates were just a moment ago. And now that it's here, all you need to do is get it hot and it will glow. And importantly, it doesn't burn away. The benefit here is that you get much more light with the same amount of fuel. This lamp does burn fuel more quickly than a Dietz lantern, but it's an order of magnitude brighter. The light is also much whiter, no longer the yellow of a flame, but a true white. In the city, where the fuel was gas, you could have much more light with fewer burners. Now you don't have to use up all the oxygen in the room, and you'll have a much smaller gas bill. In a way, this was an early energy efficiency technology. How about that? Also, the need to burn the fuels more completely in Bunsen-type burners undoubtedly created a healthier environment. It's quite interesting that this lamp produces no odor when its kerosene and flat wick compatriots all do. I had assumed that there might be some catalytic reaction going on with the gas mantle, but I haven't found any evidence for that. Instead, I think it's just the fact that the burner actually manages to burn the kerosene completely. You can even see how the flame is bluer, almost like a stovetop under the mantle, just like a Bunsen burner. While I haven't found any contemporary reports of the switch to gas mantles providing healthier indoor air, I can't imagine that didn't happen. Although this discussion is muddied by the fact that the gas mantle was invented at just about the same time that the electric light bulb was being perfected. One of the things Shivelbush mentions regarding electric light, which is largely lost today, is that the big deal of the carbon filament lamp was that finally we had an electric light that mimicked gas light. Yes, you heard that right. Electric light was around long before whoever gets to rightfully claim invention of the carbon filament lamp invented the carbon filament lamp. But the arc lights of that time were way too bright to find their way into small spaces. The carbon filament light bulb was about the same brightness of contemporary open flame gas lights. Electric light hadn't so much been invented as it was tamed. The gas mantle therefore represented a brighter than electric light, for the home anyway, for a short time. Once the tungsten filament was developed in the early 1900s, electric light achieved parity. But there was a short time where the gas mantle could legitimately be viewed as superior. And so, in a funny way, the gas mantle ended up slowing the progress of electrification. I mean, why go through the trouble of signing up for electricity when you've got gas already, you're gonna keep it for cooking, and these new mantles make it just as bright as these newfangled electric lamps, which seem scary and new? It was a pretty rational choice to ignore electricity, for a while anyway. But what about outside of cities? Rural areas certainly weren't the first in line for electrification, or indeed gas service, so portable lamps and lanterns would remain the king for quite a while, and that's the niche the Audin lamp fits into. But it's certainly not perfect. It will be hard to show this on camera, but this particular lamp seems to have a defective wick. It does not burn uniformly at all. There's a substantial hot spot on one side. Try as I might, I cannot completely tame this. I've used the included wick cleaner and even gone so far as to use an X-Acto knife to cut off a few millimeters of wick and make it level. But it's still there. One spot of the wick seems to be simply thicker than the rest, I think. It's not a huge problem, but I cannot run this lamp at its full brightness because if I turn it too high, that hot spot actually produces a visible flame that leaves the mantle, and it starts depositing unburned fuel on it. This is actually kind of fascinating because so long as this doesn't go on for too long, you can reduce the intensity and that carbon buildup will burn away. But if it does go on for too long, it could damage the mantle and indeed the lamp itself. At some point I'll replace the wick, but that is a significant downside to this style of lamp. Speaking of downsides, perhaps the biggest one for this style of lamp is that even with a perfect wick, they demand near constant attention. There's a rather small sweet spot for operating it. Too low and the mantle doesn't glow, and it's a very small distance on the wick lifter between not glowing and the flame is way too high. Since the kerosene will evaporate more quickly as the lamp heats up from cold, it gets brighter on its own in the first 10 minutes or so of operation, and in fact the instructions provided tell you to make sure you're checking on it every 30 minutes. Really, this thing is just in a very delicate balance. Take a look at this. That's terrifying. So then, it won't surprise you to learn that these things cannot be used outdoors. There's just no way you're going to get the necessary stability of the flame with really any wind at all. But the Audin lamp is, and has always been, a weird case. And that's why showcasing it here is, well, not really how gas mantles were used most of the time. The Audin lamp shows that you can use kerosene and a wick to drive a gas mantle, but the best thing to use is gas. But now, here's a question. How do you make that portable? Well, here's one option. This is a modern propane camping lantern. It's really nothing more than a modified propane torch. Instead of being a, well, torch, the gas comes out of these two orifices which have a gas mantle tied around them. This is a remarkably bright lantern, something close to 100 watts incandescent equivalent at its full brightness. But, well, these little bottles of propane are a rather recent thing. They weren't around when these lanterns were first invented. Instead, these lanterns were originally made to run on, wait for it, gasoline. Or in some countries, kerosene. Or even margarine. Wait, no, not that one. But lots of different liquid fuels could be used in lanterns like these. However, that presents a challenge. For instance, gasoline's flash point is way too low to use with a wick, unless your goal is to set yourself on fire. And besides, we don't want a wick-style flame anyway. We want a Bunsen flame. Sure, we can get that from propane because it is a gas at atmospheric pressures. Just let it out of the bottle. But how do you do that with a liquid fuel like kerosene or gasoline? Well, we'll talk about that in the next video. And we'll also talk about that thorium debacle. It's a real Thor spot for some campers out there. By the way, if you're wondering where I got an Aladdin lamp, well, much like these Dietz lanterns, these just never stopped getting made. However, at this point, they are clearly more of a collector's item. They're also not cheap, costing more than $200 for a basic lamp like this one. But unlike a Dietz lantern, they're safe-ish to use indoors. I would certainly never leave this unattended for a moment. But also, they're just much more useful by virtue of being, a bright light that doesn't smell terrible. I actually used this during a power outage, and it was pretty ideal, actually. They produce a lot of heat, so not great in the summer, but it's also not tremendously much, something like 800 or 900 watts. However, that heat is very pronounced. The narrow chimney and strong draft mean it is painful to put your hand anywhere near the top of it. Like even here, that's really painful if you can even see that. Now, that also means that the chimney needs to be made of borosilicate glass to withstand the enormous temperature swing from cold to extremely hot. The metal frame holding the mantle glows red hot at the top after it's been in use for a while. And the biggest downside to the Aladdin lamp is that you have to use kerosene. You can't use any of the various alternatives, which is, by the way, why I've been burning straight kerosene in the Dietz lanterns. That's not a huge problem, as kerosene is widely available, but you'll likely be buying it exclusively for the lamp, unless you had maybe a kerosene heater too. But really, it's just a rather niche fuel at this point. Oh, and one of my very favorite things about this, you actually blow it out. I'm serious, you don't just lower the wick all the way. If you do that, you'll notice there are still flames at the bottom. Instead, you lower it so far that it stops glowing, and then you have to disturb the draft to completely extinguish it. So, you simply cup your hand behind the chimney and blow across the top. That's what I call neat. It was in the factories. Nope, that's not in the sentence. Which, funnily enough, were devices conceived by none other by tweaking the coal distilling process and also by using different sources. No, that was correct. Why'd you stop? And also, they're much more useful by virtue. But we quickly found its various downsides. Shoot. But it's so light and fragile. How on earth are you supposed to install one? I skipped the word if. It takes the form of the fabric neck. I believe I just said fabric neck. The actual string really can be... Oops.